The clock is ticking not just for Earth, but for all of humanity. What if the key to our survival, our greatest discoveries, even our next evolutionary leap, is already hurtling through the cosmos right now? Hidden in the blueprints of 25 extraordinary space missions are secrets that could rewrite science, shatter our cosmic loneliness, or even save us from extinction. These aren't just rockets and satellites, they're time capsules of human ambition, each carrying the potential to tilt the future of our species, from a telescope that might finally answer, "Are we alone?" to a spacecraft designed to rendezvous with an interstellar visitor. These missions could change everything we know about the universe and ourselves. Buckle up, we're counting down the 25 missions that could redefine reality as we know it. Picture a cosmic time machine floating a million miles from Earth, its golden mirrors unfolding like a delicate origami masterpiece against the black void. The James Webb Space Telescope isn't just another satellite, it's humanity's most ambitious window into the past. Unlike Hubble, which showed us the universe's adolescence, Webb peers into its infancy, capturing light that's been traveling for over 13 billion years. Those shimmering hexagonal mirrors, coated in a layer of gold thinner than a human hair, act like a colossal pair of infrared goggles, cutting through cosmic dust to reveal newborn galaxies flickering to life in the early universe. But Webb's real magic, it's scanning distant exoplanets with precision never before possible, analyzing the chemical fingerprints of their atmospheres for signs of water, methane, even potential biosignatures. Imagine this one telescope could soon whisper the answer to a question that's haunted us for centuries. Are we alone? Every image it beams back isn't just data, it's a postcard from the edge of reality itself. Half a century after the last bootprints marked the moon's dusty surface, humanity is finally going back, but this time we're not just planting flags. NASA Artemis program is a cosmic game changer, a multi-stage blueprint to establish a permanent human presence on the moon. Unlike the Apollo missions, which were sprinting to the finish line of the space race, Artemis is laying the foundation for something far bolder. At its heart, the Lunar Gateway, a futuristic space station that will orbit the moon like a celestial waypoint. Think of it as a cosmic pit stop where astronauts can live, conduct research, and prepare for descents to the lunar surface. But the real vision extends beyond just short visits. Artemis aims to build sustainable habitats near the moon's south pole, where frozen water hides in shadowed craters. That water could be split into oxygen for breathing and hydrogen for rocket fuel, essentially turning the moon into a cosmic gas station. And here's the kicker, every piece of Artemis, from the heavy Liftosaurus rocket to the next-gen spacesuits, is designed with an even bigger goal in mind: Mars. The moon isn't just a destination this time, it's the ultimate training ground, the proving ground for technologies that will one day carry humans to the red planet. With Artemis, we're not just returning to the moon, we're learning how to stay. For decades, Martian soil has been the holy grail of planetary science, locked away under that rusty red sky, holding secrets no rover or orbiter could fully uncover from a distance. Now history's first interplanetary UPS delivery is in the works. NASA and ESA's Mars Sample Return mission isn't just ambitious, it's an intricate cosmic ballet involving robots, rockets, and a game of catch across 34 million miles. Right now, Perseverance is our star player, drilling into ancient lake beds and sealing pristine samples into titanium tubes with the precision of a surgeon. These aren't just rocks, they're time capsules from a wetter, warmer Mars that might have once harbored life. But here's the twist, collecting them was the easy part. The real challenge, launching those tubes off Mars without a launch pad, a team on the ground, or even a GPS signal to guide them. Enter the Mars Ascent Vehicle, a rocket the size of a mailbox that has to fire itself into orbit autonomously, meet up with a European spacecraft, and safely stow its precious cargo. One wrong calculation, and we're left waiting another decade for a second shot. If it succeeds, scientists will finally get their hands on real Martian dirt, analyzing it with Earth's most advanced labs to answer the ultimate question: did life ever take root beyond our pale blue dot? This mission isn't just about bringing home souvenirs, it's about rewriting the story of our place in the cosmos. Beneath the frozen crust of Jupiter's moon Europa lies an ocean unlike any on Earth, a vast, saltwater sea hidden under miles of ice, holding more liquid than all our planet's oceans combined. NASA Europa Clipper isn't just another spacecraft, it's a high-tech detective built to solve one of the solar system's greatest mysteries. Unlike traditional orbiters, Clipper will perform a carefully choreographed series of swoops and flybys, skimming as close as 16 miles above Europa's cracked, icy surface. Each pass is like a surgical strike, using ice-penetrating radar to map the hidden ocean's depth, while spectrometers scan for organic molecules that could hint at life. The real magic happens when its instruments detect plumes, those geyser-like sprays of water vapor erupting from Europa's fractures. If Clipper catches one in action, it might just sample alien ocean water without ever touching down. Picture this: a spacecraft analyzing the chemistry of another world's ocean while zipping by at over 14,000 miles per hour. The stakes: evidence that life might exist right now, not in some distant galaxy, but in our own cosmic backyard. Europa Clipper isn't just exploring a moon, it's hunting for the building blocks of life in a shadowy, underwater realm we've never directly seen. Imagine a world where the sky is orange, the rivers flow with liquid methane, and the ground is covered in organic dunes. Welcome to Titan, Saturn's enigmatic moon. NASA Dragonfly mission isn't just sending another rover, it's launching an 8-rotor, nuclear-powered drone designed to soar through this alien atmosphere like a robotic explorer from a sci-fi novel. Picture this: a machine the size of a small car, lifting off from Titan's icy surface on spinning blades, navigating thick, nitrogen-rich air 3 times denser than Earth's. But Dragonfly isn't just sightseeing, it's hunting for the chemical ingredients of life. This moon is a frozen time capsule, preserving prebiotic chemistry eerily similar to what might have existed on Earth before life emerged. Every landing site is a new laboratory, where Dragonfly's instruments will crack open surface samples, searching for amino acids, carbon chains, and other organic molecules that could reveal how life's building blocks form in extreme environments. What makes Titan so special? It's the only place in the solar system, other than Earth, where stable liquids flow across the surface. Except here, they're rivers of methane carving valleys into ice as hard as rock. Dragonfly will hopscotch from one scientific hotspot to another, uncovering whether Titan's complex chemistry could hint at life's origins, or even host exotic life forms adapted to its frigid, hydrocarbon-rich world. This isn't just exploration, it's a journey to an alien frontier that could rewrite the book on how life begins. While Mars and the icy moon steal headlines, another world much closer to home holds chilling secrets: Venus, Earth's twisted twin. Once imagined as a lush paradise, today it's a scorching pressure cooker with skies of acid. NASA daring duo, DaVinci Plus and Veritas, are teaming up to crack the case of how this neighbor went so wrong. DaVinci Plus isn't just an orbiter, it's a descent probe built to survive the planet's crushing atmosphere, where pressures could flatten a submarine. As it plunges through thick clouds of sulfuric acid, its sensors will dissect the toxic soup layer by layer, hunting for traces of water vapor or even noble gases that could reveal Venus' watery past. Picture this: a bullet-shaped probe screaming downward at 25,000 miles per hour, enduring temperatures hot enough to melt lead, all to answer one haunting question: did Venus once have oceans like Earth? Meanwhile, Veritas maps the inferno from above with radar so precise it could spot a parking lot on Earth. This orbiter peers through Venus' perpetual cloud cover to chart its volcanic highlands and fractured plains in unprecedented detail. Scientists suspect the planet might still be geologically alive, spewing lava from ancient volcanoes that could reshape its surface even today. But here's the real kicker: by comparing Venus' runaway greenhouse effect with Earth's own climate, these missions might give us a terrifying glimpse of our planet's worst-case future. Together Da Vinci Plus and Veritas aren't just studying another world, they're piecing together a cautionary tale. What turned Venus into a furnace, and could Earth one day follow suit? The answers might be hiding in its acidic clouds and lava-scarred plains, waiting to rewrite the story of how habitable worlds survive or die. Hidden in the silent shadows of the moon's far side lies an idea so bold it sounds like science fiction, a telescope built not on Earth, not in space but inside a crater itself. NASA Lunar Crater Radio Telescope is no ordinary observatory. Imagine a kilometer-wide dish of wire mesh suspended hundreds of meters above the floor of a perfectly round lunar crater, like a giant spiderweb woven by robots. Why go through the trouble? Because this telescope would peer into a cosmic chapter no other instrument can see: the dark ages of the universe. Here's the problem. Earth's atmosphere and our planet's endless chatter of radio noise drown out faint signals from the early cosmos. But the moon's far side, it's nature's perfect radio silence, shielded from Earth's interference, a lunar telescope could detect the ultra-faint whispers of hydrogen from a time before the first stars flickered to life, over 13 billion years ago. That signal holds clues to how the universe transitioned from darkness to light, solving mysteries about the formation of the very first galaxies. The plan is as ingenious as it is daring. Autonomous rovers would scale the crater's rim, unfurling a delicate mesh while guided by lunar gravity alone, no massive support structures, just precision engineering working in slow motion. Once complete, this silent sentinel could reveal cosmic history in a way no Earth-bound antenna ever could. It's not just about building a telescope, it's about opening a window to the universe's birth, all from the quietest listening post humanity has ever known. Deep in the asteroid belt between Mars and Jupiter floats a cosmic oddity, an object so strange it shouldn't exist. Asteroid 16 Psyche isn't just another space rock, it's a gleaming, metallic world roughly the size of Massachusetts, made almost entirely of iron and nickel. This isn't rubble left over from the solar system's formation, it's something far more tantalizing. Scientists suspect Psyche might be the shattered heart of a failed planet, a naked core stripped of its rocky shell by violent collisions billions of years ago. NASA's mission to this metal giant is like sending a time machine back to our solar system's most chaotic era. The spacecraft, aptly named Psyche, will brave a 6-year journey across 2.5 billion miles to reach its target. Once there, it won't land or scoop samples. Instead, its suite of instruments will orbit just 70 miles above that alien surface, mapping every crater and ridge with gamma rays, neutron spectrometers, and a high-resolution imager. What makes this mission revolutionary? Earth's own molten core, buried under thousands of miles of rock, holds the secrets to our magnetic field and plate tectonics, but will never dig that deep. Psyche offers a cheat code, a chance to study a planetary core up close, frozen in time. Is it solid or molten? Does it still generate a magnetic field? The answers could rewrite textbooks on how rocky planets like ours form and evolve, but there's another twist. Psyche's metallic composition makes it staggeringly valuable. The iron alone would be worth quadrillions if mine, not that anyone's planning to. Beyond treasure, this mission probes something deeper, the violent childhood of our solar system, written in the scars of a drifting metal world. This isn't just about an asteroid, it's about decoding the hidden blueprint of planets, including our own. The idea sounds ripped straight from a starry-eyed dream, a fleet of spacecraft no bigger than a postage stamp, hurtling toward another star at speeds once reserved for science fiction. Breakthrough Starshot isn't just ambitious, it's a radical reimagining of interstellar travel, shrinking probes down to grams and propelling them with the gentle but relentless push of lasers. At the heart of this audacious plan lies the light sail, an ultra-thin, reflective sheet thinner than a soap bubble. Instead of bulky rockets, these nanocraft would catch a high-powered laser beam fired from Earth, riding its momentum like a cosmic surfer. The acceleration would be brutal, 0 to 20% the speed of light in mere minutes, a velocity that would get these tiny explorers to Alpha Centauri in just over 20 years. That's a blink of an eye compared to the millennia traditional rockets would need, but the challenges are as staggering as the vision. Each nanocraft must survive intense radiation, micrometeoroid impacts, and decades of deep space loneliness while packing cameras, sensors, and transmitters into a spec-sized package. Then there's the laser array itself, requiring gigawatts of power, a synchronized phalanx of beams stretching across miles, and precision so exact it could hit a sail thousands of miles away. The payoff close-up images of Proxima Centauri b, the potentially Earth-like world orbiting our nearest stellar neighbor. Starshot wouldn't just send back data, it would rewrite humanity's place among the stars, proving that even the vast distances between suns aren't insurmountable. This isn't just a mission, it's a test of whether we can reach beyond our solar system within a single generation, and if it succeeds, the stars might finally be within our grasp. Forget everything you know about space telescopes, because LUVOIR isn't just an upgrade, it's a quantum leap. Imagine a mirror so vast it could swallow Hubble's entire light-collecting area 15 times over, its segmented panels unfolding in orbit like a colossal golden flower. This isn't just about seeing farther, it's about seeing sharper. LUVOIR's staggering resolution could zoom in on an exoplanet 20 light-years away and map continents on its surface, like spotting a dime from 30 miles. But the real magic lies in its hunt for life, where Hubble glimpses blurry dots and Webb analyzes faint chemical traces. LUVOIR would directly photograph Earth-like worlds crisp enough to detect oceans, clouds, even vegetation. Its spectrometers could dissect the light filtering through alien atmospheres, hunting for the telltale cocktail of oxygen, methane, and water vapor that screams life. Picture this, a telescope so powerful it might catch the reflected glow of city lights on a distant world, or seasonal changes in alien forests. The challenges. Engineering a mirror that massive requires robotic precision, each hexagon aligning within nanometers to act as a single flawless surface. Then there's the orbit, a gravitational sweet spot a million miles out, where Earth's glow won't drown out delicate signals. But if it launches in the 2030s as planned, LUVOIR could do more than find habitable planets. It might answer the ultimate question: is anyone else out there right now, looking back at us? This isn't just another telescope, it's humanity's best shot at turning specks of light into worlds, and maybe, just maybe, neighbors. High above our planet, where sunlight never fades behind clouds or sets below the horizon, an audacious energy revolution is taking shape. Space solar power isn't science fiction anymore, it's a global race to harness the sun's pure, uninterrupted rays from orbit and beam clean energy straight down to Earth. Picture vast solar arrays, each spanning football fields, soaring in perfect sync with our planet's rotation. Unlike ground-based panels, these orbital farms soak up sunlight 24 hours a day, converting it into microwave or laser beams aimed with pinpoint accuracy at receiving stations below. The engineering hurdles, they're as towering as the ambition itself. Transmitting energy across hundreds of miles of atmosphere requires efficiency. We've only just begun to master any loss in the beam could make the system impractical. Then there's the cost of launching thousands of tons of hardware into space. Though reusable rockets are slashing those barriers fast, countries from Japan to the US and China are pouring resources into prototypes, betting on a future where desert-based retinas, those massive, grid-like receivers, could one day power entire cities without a single smokestack in sight. The implications are staggering. Imagine drought-stricken regions gaining access to unlimited clean water, powered by sunlight harvested in space, or disaster zones instantly receiving emergency energy without waiting for repaired infrastructure. Critics argue the risks like potential beam misalignment aren't trivial, but the promise of a carbon-free baseload energy source has even skeptics intrigued. This isn't just about keeping lights on, it's about redefining how civilization taps into the cosmos itself to break free from fossil fuels. The technology may be in its infancy, but the dream is clear: a world where energy rains down from the sky, as reliable as sunrise. Mars has always been the great what-if in humanity's cosmic story, but what was once science fiction is now inching toward reality. At the forefront is SpaceX's Starship, a stainless steel behemoth designed not just for quick visits, but for delivering the first permanent settlers to the Red Planet. Picture this: a fleet of these colossal rockets, each carrying 100 passengers or more, touching down in the rusty dust to establish outposts that grow into towns, then cities. Starship isn't just a spacecraft, it's a self-contained habitat, with enough room for crews to live and work during the grueling 6-month journey, but the real challenge begins after landing. Surviving on Mars means solving problems we've never faced before. Radiation from solar flares and cosmic rays bombards the surface, unblocked by a thick atmosphere or magnetic field. The solution: burying habitats under Martian soil, using the planet itself as a shield. Others propose inflatable modules lined with water-rich gel, nature's perfect radiation absorber. Then there's the air issue. Mars' atmosphere is lethally thin, mostly carbon dioxide. Pioneers will rely on machines that split CO2 into breathable oxygen, while hydroponic farms recycle every drop of water and generate food under artificial suns. But SpaceX isn't alone in this vision. NASA Mars Dune Alpha simulates life on the planet right here on Earth, where crews test survival strategies in a 3D printed habitat. Meanwhile, European architects dream of mushroom-based construction, using mycelium to grow sturdy, lightweight structures from local materials, the ultimate goal. Transforming Mars from a hostile wasteland into a second home, one where future generations might stroll under pressurized domes, gazing at Earth as a pale blue star in their twilight sky. This isn't just about planting flags, it's about planting roots, and with every test flight and prototype, the dream of a Martian civilization becomes less fantasy and more inevitable. Hidden from Earth's relentless radio chatter lies an unexplored frontier of cosmic silence, the Moon's far side. Here, where our planet's noise can't reach, scientists envision the ultimate eavesdropping post for the universe's oldest whispers. Unlike traditional telescopes that struggle against humanity's electronic buzz, a lunar far-side observatory would bask in pristine quiet, tuned to frequencies no Earth-bound dish could ever hear clearly. The target: primordial gravitational waves, ripples in spacetime itself, left over from the Big Bang's first chaotic moments. These faint tremors carry clues about the universe's birth, but they're drowned out by Earth's atmosphere and our own radio transmissions. On the Moon's shielded surface, ultra-sensitive antennas could finally detect these cosmic echoes, potentially revealing what happened in the first trillionth of a second after creation. Placing a telescope there isn't as simple as parking a rover. The far side's extreme isolation means no direct communication with Earth. Every signal must bounce off relay satellites. Engineers are exploring autonomous setups where robotic landers deploy sprawling arrays of thin, conductive wire mesh to form massive antennas. Some designs even propose using lunar soil to construct natural dish structures, turning the Moon's terrain into part of the telescope itself. The payoff could be revolutionary. Detecting these primordial waves might confirm theories about cosmic inflation, the idea that the universe expanded faster than light in its first instant. It's like uncovering the universe's baby pictures, frozen in spacetime itself, and unlike optical telescopes that see only the aftermath of cosmic events, a lunar radio observatory would listen to the very vibrations of creation, offering a backstage pass to the Big Bang's opening act. This isn't just about building a telescope, it's about unlocking a hidden channel to the dawn of everything, from a vantage point no earthly instrument could ever match. The far side's silence isn't empty, it's a blank page waiting for the universe's oldest story to be heard at last. Picture a cosmic tugboat in the void, not towing ships but steering mountains. Asteroid redirect missions sound like the plot of a disaster movie, but they're fast becoming one of humanity's most practical space endeavors. NASA's scrapped AR mission laid the groundwork, proposing to pluck a boulder off an asteroid and gently nudge it into lunar orbit, a test run for deflecting genuine threats. While that plan was shelved, the lessons learned now fuel global efforts to turn planetary defense from science fiction into routine engineering. Today, international teams are designing spacecraft that could gently push an asteroid off course using nothing but their own gravitational pull. Think of it as celestial persuasion, a probe hovering near a space rock for months or years, its tiny but steady gravity slowly altering the asteroid's trajectory. No explosives, no Hollywood heroics, just orbital mechanics at work. The European Space Agency's Hera mission, launching soon, will scout the crater left by NASA DART impact test, studying how real asteroids respond to collisions. Meanwhile, Japan's Hayabusa 2 proved we can land on and sample these rogue rocks with pinpoint precision, but redirecting asteroids isn't just about doomsday scenarios. The same tech could one day park resource-rich space rocks into stable orbits, turning them into cosmic gas stations or mining outposts. Imagine a future where water extracted from asteroids fuels deep space missions, or rare metals mined off their surfaces revolutionize industries back on Earth. The challenge is calculating each nudge with flawless accuracy. One wrong move, and you might send a rock spiraling toward Earth instead of away. This isn't just about playing billiards with celestial bodies, it's about mastering the delicate art of moving mountains, one gentle tug at a time. Whether for survival or ambition, redirecting asteroids could define our next chapter as a spacefaring species, and with every mission, we're proving that even the heavens aren't beyond our reach. For nearly 4 decades, one planet in our solar system has remained stubbornly out of reach, a pale blue ice giant, spinning on its side like a cosmic top. Uranus, with its bizarre 98-degree tilt and chaotic magnetic field, holds secrets that could rewrite planetary science. Now, after decades of anticipation, NASA proposed Uranus orbiter and probe mission stands ready to crack the code of this enigmatic world. The mission's crown jewel, a car-sized probe plunging into Uranus' frigid atmosphere, enduring pressures that would crush a submarine as it beams back the first direct measurements of its composition. Unlike Jupiter and Saturn, rich with data from dedicated orbiters, Uranus remains a blank spot on the map. Its interior structure, wild magnetic field, and even the potential heat source driving its storms all locked in mystery. But the surprises don't stop at the planet itself. Among its 27 moons, Miranda stands out like a shattered puzzle. This icy world sports canyon walls 12 miles high, deeper than the Grand Canyon, and terrain so jumbled it looks like it was smashed and hastily reassembled. Scientists suspect liquid oceans might lurk beneath its fractured crust, kept warm by gravitational squeezing from Uranus. If true, Miranda could join Europa and Enceladus as a sanctuary for extraterrestrial life, hiding in our own cosmic backyard. The mission faces brutal challenges. At nearly 2 billion miles away, sunlight is 900 times dimmer than on Earth, forcing solar panels the size of tennis courts or relying on nuclear power. Communication delays stretch to almost 3 hours each way, demanding spacecraft smart enough to handle crises autonomously, yet the payoff could be monumental. Understanding why Uranus' magnetic field flips on and off like a faulty light switch might reveal how exotic ices and supercritical fluids behave under extreme pressures, clues to the thousands of similar ice giants orbiting distant stars. And if Miranda's underground oceans prove real, it would transform our search for life beyond Earth. This isn't just about visiting a new planet, it's about solving a celestial riddle that's puzzled astronomers since the telescope's invention. The clock is ticking to unveil the solar system's last great unknown before another generation slips by. Imagine stepping into a celestial elevator, no rockets, no bone-rattling G-forces, just a smooth ascent from Earth's surface straight to space. The concept of a space elevator sounds like pure science fiction, but recent breakthroughs in materials science are bringing this dream tantalizingly close to reality. Instead of burning thousands of tons of fuel to reach orbit, we could one day ride a carbon fiber tether stretching 22,000 miles into the sky, anchored by a counterweight among the stars. The biggest obstacle, building a cable strong enough to handle the mind-bending stresses involved. Ordinary steel would snap under its own weight long before reaching the necessary length. That's where carbon nanotubes come in. These microscopic threads are up to 100 times stronger than steel yet lighter than aluminum. The catch, we've only been able to grow them in lab samples a few centimeters long. Scaling up to thousands of miles would require manufacturing techniques that don't exist yet, like molecular 3D printers weaving atomic bonds into unbreakable strands. Yet the vision doesn't stop at Earth. Some engineers propose a lunar version first, where the moon's weaker gravity and lack of atmosphere make construction far simpler. A lunar space elevator could stretch from the moon's surface to a Lagrange point, a gravitational sweet spot where Earth and the moon's pulls balance out. Instead of rockets ferrying mined resources from the moon's surface, robotic climbers could glide up this cosmic highway, slinging raw materials into space for orbital factories or deep space missions. Critics argue the economics are still speculative, but the potential is staggering. A single space elevator could slash launch costs from thousands of dollars per pound to mere pennies, opening the cosmos to everyday access. Imagine scientists commuting to orbital labs, tourists boarding elevators to zero-gravity hotels, or solar power stations assembled with materials hauled up effortlessly. The challenges are immense: space debris, lightning strikes, even the risk of the cable snapping, but the payoff could rewrite humanity's relationship with the stars. This isn't just about building a taller version of the Burj Khalifa, it's about constructing a bridge between worlds, one atom at a time, and while the full Earth elevator might still be decades away, every experiment with nanotube fibers or lunar prototypes brings us closer to turning this sci-fi fantasy into tomorrow's commute. The elevator to the cosmos is waiting, we just need to invent the cable. Bursting through the icy crust of Saturn's tiny moon Enceladus are towering plumes of water vapor, shooting hundreds of miles into space like cosmic geysers. These aren't just spectacular eruptions, they're direct samples from a hidden ocean buried beneath miles of ice, offering scientists a free ride to analyze alien water without ever drilling. NASA proposed Enceladus Life Finder mission aims to do just that, sailing straight through these shimmering jets, hunting for the chemistry of life in a place where sunlight never reaches. What makes this moon so special? Beneath its frozen shell lies a global ocean, kept liquid by the gravitational squeeze of Saturn itself. Hydrothermal vents on the seafloor might be churning out minerals and warmth conditions eerily similar to Earth's deep-sea vents, where life thrives without sunlight. ELEF's instruments would act like molecular detectives, sniffing out complex organic compounds, amino acids, and even potential metabolic byproducts floating in those plumes. The real prize, finding patterns in molecules that couldn't form without biological activity, something like the chemical fingerprints of microbial life. Unlike rovers that dig or orbiters that observe from afar, ELEF would get up close and personal, diving through the plumes at just 15 miles above the surface. Each pass would capture thousands of ice particles, vaporizing them instantly to reveal their secrets. Some scientists believe Enceladus Ocean could be the most habitable place beyond Earth, warmer, saltier, and richer in energy than Mars or Europa. If ELEF detects the right cocktail of compounds, it might not just hint at life, it could prove it exists right now in our own solar system. The stakes couldn't be higher. Confirming life on Enceladus would mean biology isn't a fluke of Earth, it's a cosmic imperative, thriving wherever conditions allow, and with every geyser spewing free samples into space, this tiny moon is practically begging us to take a closer look. One daring mission could answer the ultimate question: are we alone, or is the universe teeming with life just waiting to be found? Here's how humanity could turn the sun itself into the most powerful telescope ever imagined. No mirrors or lenses required, just pure physics at cosmic scale. Einstein predicted it over a century ago. Massive objects like stars warp spacetime so dramatically that they bend light around them, acting like colossal lenses. Now scientists are racing to harness this phenomenon, using our own sun as a gravitational magnifying glass to zoom in on distant exoplanets with unprecedented clarity. The math is staggering. Position a spacecraft perfectly along the line where the sun's gravity focuses light from a target exoplanet, and you'd achieve magnification up to 1,000 times sharper than today's best telescopes. At that resolution, a planet 100 light-years away wouldn't just be a pixel. You could map its cloud patterns, spot continents, even detect signs of agriculture or city lights. The catch: this sweet spot, called the focal line, lies a mind-bending 550 times farther from the Sun than Earth, roughly 14 times Pluto's distance. Reaching it would take decades with current propulsion. Engineers are already sketching spacecraft designed for this epic journey. Picture a probe no bigger than a washing machine, equipped with a coronagraph to block the sun's blinding glare, inching toward the focal line at a snail's pace. Once there, its sensors would stitch together an image from the distorted Einstein ring of light bent around our star, like assembling a cosmic jigsaw puzzle. The technical hurdles are immense: maintaining nanometer-level precision over billions of miles, compensating for solar flares warping the lens effect, and decoding atmospheric interference across light years. But the payoff: a front-row seat to another Earth. Unlike inferring conditions from spectral data, this mission could deliver actual photographs of alien landscapes, rainforests, deserts, or perhaps something beyond our imagination. It's not just about finding life, it's about seeing it in detail no other technology could match. The solar gravitational lens isn't just a telescope, it's humanity's chance to gaze across the galaxy and ask, face to face, is anyone home? And with prototypes already in early testing, this audacious idea might leap from equations to reality within our lifetimes. The sun, our oldest companion in the sky, could soon become our greatest window to the stars. Tucked away in the moon's permanently shadowed craters lies a treasure more valuable than gold: sheets of pristine water ice, frozen solid for billions of years. These aren't just geological curiosities. They're the key to unlocking humanity's future as an interplanetary species. Lunar ice mining isn't science fiction anymore, it's a practical blueprint for turning our barren neighbor into a cosmic gas station. Here's why this changes everything. Water isn't just for drinking, it's the universal space currency. Split it into hydrogen and oxygen, and you've got breathable air for astronauts and potent rocket fuel. A single ton of lunar ice could produce enough propellant to send missions to Mars without hauling every drop from Earth's gravity well. The math is staggering. Launching a gallon of water from our planet costs tens of thousands of dollars. Harvesting it on site, pennies by comparison, but extracting this icy bounty isn't as simple as chipping glaciers. These craters are some of the coldest places in the solar system, dipping below -400 degrees Fahrenheit. Proposals range from solar-powered rovers equipped with drills and heaters to massive mirrors reflecting sunlight into the shadows, gently warming the ice for collection. The real challenge: doing it all in bulky spacesuits or with autonomous bots, navigating terrain where darkness never lifts. The first lunar miners won't just be prospectors, they'll be industrial chemists operating mini refineries that electrolyze water into fuel. Imagine depots scattered across the moon's poles, stocked with tanks of hydrogen and oxygen, ready to power rockets hopping between Earth, lunar orbit, and beyond. This isn't just about sustainability, it's about rewriting the economics of space travel. Suddenly, the moon becomes more than a destination, it's the ultimate springboard, slingshotting humanity deeper into the cosmos than we've ever dreamed. And the ripple effects don't stop there. Lunar ice could nurture greenhouse domes, shielding crops from radiation while recycling every drop of moisture. Some companies even envision piping oxygen directly into habitats, creating self-sustaining colonies under the stars. What starts as a mining operation could blossom into humanity's first true foothold off Earth, all because we cracked the code of harvesting ancient ice in the dark. At the solar system's frozen edge, where sunlight is little more than a faint glimmer, Neptune's moon Triton defies expectations. This isn't just another icy world, it's a cosmic oddity spinning backward, spewing nitrogen geysers into space, and possibly hiding an ocean beneath its cracked surface. A Neptune orbiter mission wouldn't just explore a moon, it would unravel the mysteries of a kidnapped world. Triton shouldn't exist here. Its retrograde orbit, the only large moon in the solar system moving opposite its planet's rotation, screams interloper. The leading theory: Neptune's gravity snatched it from the Kuiper belt billions of years ago, making it a primordial time capsule from the outer solar system's chaotic past. But what makes Triton truly bizarre are its cryovolcanoes, erupting plumes of nitrogen gas and dark organic particles 8 miles high, caught in stunning detail by Voyager 2 back in 1989. No other moon in our system shows such violent activity this far from the sun's warmth, yet the real prize might lurk beneath Triton's frozen crust. Tidal heating from Neptune's relentless pull could maintain a liquid water ocean, sandwiched between layers of ice and rock. If so, Triton joins Europa and Enceladus as a potential sanctuary for alien life, but with a twist: its ocean would be laced with ammonia, lowering the freezing point and creating chemistry unlike anything on Earth. Imagine extremophile microbes thriving in the dark, fueled by hydrothermal vents in an ocean older than multicellular life back home. A dedicated Neptune orbiter could finally crack Triton's code, mapping its geysers with infrared eyes and probing its interior with radar. But reaching this distant outpost won't be easy. Even with a gravity assist from Jupiter, the journey would take 15 years, requiring a spacecraft tough enough to survive cosmic radiation and smart enough to work autonomously when signals from Earth take 4 hours each way. The payoff: understanding how captured worlds like Triton shape planetary systems, and whether life could emerge in the darkest, coldest corners of the cosmos. This isn't just about Neptune's moon, it's about rewriting the story of how solar systems steal, freeze, and maybe even awaken worlds, and with every geyser Triton erupts, it's practically begging us to take a closer look. While most spacecraft cling to the warmth of the inner solar system, one bold mission dares to venture where no human-made object has gone before, into the frigid, uncharted void between the stars. The interstellar probe isn't just another satellite, it's a cosmic trailblazer designed to push past 1,000 astronomical units from the Sun. So far out, Earth would appear as nothing more than a pale blue speck lost in the darkness. Unlike Voyager's accidental journey into interstellar space, this probe would be purpose-built to explore the mysterious boundary where the Sun's influence finally fades. That transition zone, called the heliopause, acts like a protective bubble shielding our solar system from galactic radiation, but we barely understand how it works. By racing outward at speeds up to 7 times faster than Voyager, the interstellar probe could map this invisible frontier in high resolution, studying alien cosmic rays and the interstellar medium with instruments far more advanced than those of the 1970s. The key to this unprecedented speed: cutting-edge propulsion. Solar sails, thinner than a human hair but spanning nearly half a mile, could catch the sun's momentum like a cosmic kite, no fuel required, just the gentle but relentless push of photons. Alternatively, nuclear electric propulsion might harness the steady thrum of fission reactors, accelerating the probe to velocities that would leave traditional chemical rockets in the dust. Either way, this mission would eclipse all previous distance records, venturing so far that data transmissions could take weeks to crawl back to Earth. What lies beyond the heliopause? A realm of frozen primordial particles, clues to how stars and planets form, and perhaps even traces of nearby exoplanet atmospheres carried on the interstellar breeze. The interstellar probe could also turn its gaze backward, capturing a family portrait of our solar system from the outside, a perspective no mission has ever achieved. This isn't just about setting records, it's about crossing an invisible threshold, proving that humanity's reach can extend beyond our star's cradle and into the galaxy at large. And when it finally pierces that boundary, decades from now, the tiny spacecraft will carry with it the quiet hope that one day, something far more ambitious might follow, a vessel bearing not just sensors but explorers. The interstellar probe is more than a mission. It's the first intentional step into the cosmic ocean, testing the currents before we set sail. Floating a million miles apart in perfect formation, 3 spacecraft will soon form the most precise measuring device ever built, not to study light or particles, but to catch invisible ripples in the fabric of reality itself. Meet LISA, the Laser Interferometer Space Antenna, a next-generation gravitational wave detector designed to listen to the collisions of supermassive black holes so distant, their echoes have traveled billions of years to reach us. Unlike ground-based observatories like LIGO, which detected fleeting tremors from stellar mass black holes, LISA triangular constellation will orbit the Sun in synchronized harmony. Each side of this cosmic triangle stretches 1.5 million miles wide, enough to span the distance from Earth to the Moon 6 times over. At their core, a pair of floating gold-plated cubes, isolated from all forces except gravity itself, bouncing laser beams between them with atomic precision. When a gravitational wave passes through, it will stretch spacetime itself, altering the laser's travel time by less than the width of an atom, and LISA instruments will catch that minuscule wobble like a seismograph for the universe. They quarry the universe's most cataclysmic events, while ground detectors hear the chirps of black holes dozens of times the Sun's mass. LISA will tune into the deep bass notes of monsters, supermassive black holes millions, or even billions of times heavier than our Sun. These titans lurk at the hearts of galaxies, and when they spiral toward collision, their mergers shake the cosmos with energy greater than all the stars in the observable universe combined. LISA could catch them years before the final crash, tracking their slow orbital dance with unrivaled clarity, but the surprises don't stop there. This space-based ear might also detect the faint hum from the Big Bang's earliest moments, a primordial vibration imprinted on space-time itself. Or exotic objects like cosmic strings, theoretical defects in the universe's structure thinner than an atom but stretching across galaxies. Every event LISA captures will be a snapshot of gravity's purest form, untainted by dust, gas, or the messy physics of stars and planets. Slated for launch in the 2030s, LISA isn't just another observatory. It's a revolution in how we perceive the universe, one that will transform gravity from an invisible force into a symphony we can finally hear. The cosmos has been vibrating all around us since the dawn of time. At last we're building the instrument to listen. Forget floating awkwardly in zero gravity. What if life in space felt just like home, with gravity keeping your coffee in the cup and your bones strong? That's the promise of artificial gravity stations, where entire habitats rotate like slow-motion carousels to create a force mimicking Earth's pull. NASA's decades-old Nautilus X concept first proved the idea wasn't sci-fi. A sprawling, donut-shaped station spinning just fast enough to keep astronauts' muscles from withering during long missions. But today's designs go even further. Private ventures like Orbital Assembly's Pioneer Station plan to house hundreds in luxury apartments along a rotating outer ring, where centrifugal force substitutes for gravity. The science is surprisingly simple. Spin a habitat at the right speed, and inertia pushes objects and people outward against the interior walls, creating the illusion of weight. Too slow and astronauts would stumble like they're on a low-gravity moon. Too fast and the Coriolis effect could make every head turn nauseating. The sweet spot. A wheel roughly the size of a football field rotating at 8 RPM, generating comfortable artificial gravity while minimizing motion sickness. But the real breakthrough isn't just comfort, it's health. Prolonged weightlessness wreaks havoc on the human body, leaching calcium from bones, weakening heart muscles, and even blurring vision as spinal fluid redistributes. Artificial gravity could erase those risks, making multi-year missions to Mars or decades-long space habitation viable. Picture astronauts tending hydroponic gardens under simulated sunlight, jogging along a curved track where down is always outward, and sleeping in beds that don't require straps, all while the station silently pirouettes against the starry backdrop. The challenges: engineering structures massive enough to spin smoothly without wobbling, and ensuring docking ports stay stable for arriving spacecraft. But with prototypes already in development, the dream of truly sustainable space living is closer than ever. These stations won't just be waypoints, they'll be blueprints for the first cities beyond Earth, proving that humanity can thrive among the stars without sacrificing the gentle tug of gravity we evolved to need. The future of space habitation might not involve floating at all, just a steady, familiar pull beneath our feet, reminding us of home even in the void. Imagine a world where spies, hackers, and eavesdroppers suddenly hit a wall, not a digital one, but a barrier built on the bizarre laws of quantum physics. This isn't science fiction, it's happening right now, thanks to quantum communication satellites revolutionizing how we send secrets across the globe. At the forefront is China's Martian satellite, a silent orb in the night sky performing mind-bending experiments that could make traditional encryption look as flimsy as a padlock. Here's the magic at work: unlike normal signals that can be copied or intercepted, quantum communication relies on photons, single particles of light, that change their state if anyone tries to peek. It's like sealing a letter with wax that melts if touched, leaving undeniable proof of tampering. Martian proved this in orbit, beaming entangled photons between ground stations over 700 miles apart, a feat impossible on Earth due to atmospheric interference. These particles, linked by quantum entanglement, act like cosmic twins. Change one, and its partner instantly mirrors that change, no matter the distance. The implications are staggering. A future quantum internet could link continents with unhackable connections, safeguarding everything from military secrets to financial transactions. Martian has already demonstrated secure video calls between Beijing and Vienna, with encryption keys generated by the satellite itself. No supercomputer could crack this system, not even with centuries of brute force calculation. Quantum physics itself guarantees the security. But the challenges are as vast as the promise: atmospheric turbulence, satellite alignment errors, and even the delicate nature of quantum states themselves threaten to disrupt signals. Yet with every successful test, we move closer to an era where privacy isn't just a policy, it's woven into the fabric of the universe. And as more nations race to launch their own quantum satellites, a new front in the battle for cybersecurity is unfolding, not in server rooms, but in the silent expanse of space. The next revolution in communication won't rely on faster processors, it'll depend on photons dancing to the strange tune of quantum mechanics, high above our heads. Picture this: within our lifetime, humanity could wake up to undeniable proof that we're not alone in the universe, not from blurry UFO footage, but from a vial of Martian soil analyzed by robots, or a spectrometer's readout from a plume on Enceladus. These missions aren't isolated quests, they're threads in a grand cosmic tapestry, weaving toward answers that could redefine our place in the cosmos. Finding extraterrestrial life, even in microbial form, would shatter the illusion of Earth's uniqueness, proving that life isn't a fluke, it's a cosmic inevitability. But the vision stretches beyond discovery. Each mission to the Moon and Mars is a stepping stone toward something monumental, turning humanity into a multi-planetary species. Lunar ice mining could fuel interplanetary ships, while Martian habitats test technologies for self-sustaining colonies. SpaceX's Starship and NASA Artemis aren't just about planting flags, they're rehearsals for a future where a single catastrophe on Earth doesn't spell the end for human civilization. The lessons learned there: how to grow food in regolith, shield against radiation, or recycle every drop of water are survival skills for an interstellar future. And then there's Earth itself. Orbiting solar farms could beam clean energy to power grids day and night, breaking our dependence on fossil fuels without sacrificing a single acre of land. Asteroid mining might unlock rare metals for green technologies, while quantum satellites secure a global internet immune to hacking. these aren't just science projects, they're lifelines, offering solutions to crises that once seemed insurmountable. The beauty of these missions lies in their synergy. A telescope like LUVOIR could spot an exoplanet's oxygen-rich atmosphere, while a solar gravitational lens zooms in to reveal its coastlines. Meanwhile, breakthroughs in propulsion from projects like Breakthrough Starshot might one day carry our probes, and eventually us, to those distant shores. It's a domino effect. Each discovery fuels the next, accelerating our progress faster than we ever imagined. So today's headlines focus on individual launches or planetary flybys, the bigger picture is quietly taking shape. These missions are the foundation stones of a future where humanity doesn't just gaze at the stars, we reach for them, thrive among them, and perhaps even share them with other forms of life. The universe is no longer a distant frontier, it's a challenge we're finally ready to meet. As we stand on the threshold of a new cosmic era, it's worth pausing to reflect on how far we've come and how much further we might go. These 25 missions aren't just about rockets and robots, they're about rewriting the story of what it means to be a spacefaring civilization. Whether it's the faint whisper of gravitational waves from colliding black holes or the first snapshot of an alien coastline through a solar lens, every discovery has the power to reshape our understanding of the universe and our place within it. Think of the generations before us who gazed at the night sky with wonder but lacked the tools to explore it. Today, we're the lucky ones, alive in an age where science fiction is becoming science fact, where the impossible is now just a matter of engineering and time. The missions we've covered aren't endpoints, they're stepping stones. The moon will become a launch pad, Mars a second home, and the stars themselves no longer out of reach. But here's the most exciting part. The breakthroughs we'll celebrate tomorrow are being dreamed up today. Maybe it's the Europa Clipper finding signs of life in an alien ocean, or a quantum satellite making unhackable communication the global standard. Perhaps it's a young viewer watching this very video who will one day design the spacecraft that finally reaches Alpha Centauri. The universe is vast, but humanity's curiosity is limitless. Every mission we launch, every question we chase is a declaration that we refuse to be confined to one planet, one star, or even one reality. So stay curious, stay hopeful, and who knows? The next time we meet, it might be to discuss the mission that changed everything, and the one after that, and the one after that. The cosmos is waiting. Let's go explore it together.